All right. Well, we've worked our way back to integration here now. We're going to be talking about double integrals. And so first of all, let me recall with you here what our single integrals meant, and then we'll double it up. See what double integrals will mean. Okay, so if I was talking about an integral from a to b, f of x dx, that meant, graphically speaking, what? This is y equals f of x. Then the integral from a to b would be the area under the curve, or between the curve and the x-axis is, I guess, technically the way we would speak about that. And so, yeah, we found several integrals, different types of techniques to use there, but anyway, that's what it meant. Now, to even go back further, how did we arrive at this being the area under the curve? Remember, we used the rectangles, right? We divided up a to b, we divided up into subintervals. I think we did n subintervals, how many ever we wanted, and then we took the right-hand endpoints or left-hand endpoints and gave us those. And so yeah, we summed all those up. Say we went I, if this is x sub I, then I, we ran 1 to n, and point we chose, or whatever sample point we chose. You could use right endpoints, left endpoints, midpoint, up, and that gives us a pretty good approximation of my curve, area under the curve. But to get it precisely equal to, we did the limit as n went to infinity, right? Made infinitely many rectangles. Okay. Just some rehashing of what we did for that. Okay. So in 3, okay, we've got we've got a surface, and we're going to go from a to b in x, and then from c to d in y. And so that defines this, what they call a region R. And so we're going to have to go in two directions here. So instead of x running from a to b, we've got to go, y goes from c to d also. X still goes from a to b, but y has to go from c to d. All right, and so then we have this surface here. Let me see if I can draw something similar to what I've got on my paper here. So we've got this surface. And that's our function in x and y, or two-variable function. And so that defines some surface. And so over this region then, what we find is, do a real good job of that. So what we find, let me do, let's see. Okay. Make these a little bit straighter so it makes a little more sense. Okay. So what we find when we do this so-called double integral is we're going to find the volume under the curve, or between the curve and the, okay? That's just a little we can define. We've defined it on a rectangular region here, and so two ways they'll represent it. Just two different notations means the same thing. All right, now let's think about how we can arrive here at similar to our two-dimensional counterpart there. So what we have to do is, just like we divided the x-axis into subintervals, here we have to divide our r up into sub-rectangles, I guess we call it. So let me just kind of draw this out. All right, so here's our r in the xy plane. Focus in on it. All right, so I'm going to divide that into sub-rectangles. And, of course, what you have to do is divide x up into subintervals from A to B. So we divide it into n subintervals. And then the y from C to D, same thing, divide that, but we don't have to divide it up into the same amount. So we can do m subintervals. Could do the same amount, but we don't have to. So let's just say we do this one this way, and then this one. Put the same amount there anyway, didn't I? Try to do it differently. Okay. All right. So we've got different amounts there. So this we'll just call x sub I, and then this one we'll call y sub j. What we've got is all these. Get specifically, if you go at a corner, you can get a nice point there. But here's what they do. All right, so this one right here, let's just call this one r sub I j rectangle. X sub I is here, y sub j is here, so that's going to be r sub I j. Okay. All right. And so what we do then is, to approximate this volume, is we take each of these subintervals. And then we're going to pick a point out of each one, because we could choose a corner on the one that we'll do here in a second. We're going to choose a corner, but you could do a midpoint in both directions, but it could vary. Little star notation there. Okay, and so what we're going to do is take each one of those, and so here's our translate it kind of over to here. Let's draw that Rij rectangle. And then that gets shot up to the surface there. Of course, it's not going to match the exact curvature there, but it is going to be something we can. So this would be this. This would be that. And so our little Rij rectangle, we shoot that up to our surface there. I drew it probably a little too big, but that that's what we've got there. And so each one of these thin rectangular boxes, we can calculate the volume. So let's call it V sub I. I think that's what I'm going to call it. So each of those V sub i's, Vij or whatever you want to call it, is how do we come about the volume there? Well, you need to take the length times the width times the height. Height's the easy one, because that would just be whatever the function value is at that particular point. So f x sub I j star comma y sub I j star. Change in x, so it'd be delta x and delta y here, wouldn't it? Whatever our delta x, whatever our delta y is. Well, they call that delta x times delta y. They refer to that as delta A. Yep. That's just the area of region R that we're talking about. Okay. All right, well, if we then sum up all of those, then the volume that I have represented here is approximately equal to the sum of all these, right? Now, here's the thing. As far as the sum goes, don't I have two things working? I've got a sum for I and for j. So I've got two sums. So I've got to sum the i's from 1 to n. That's our x. And then I've got to sum our j's from 1 to m. And then each one of those has a particular sample point associated with it. Okay, so that gives us the approximate value. Because, like I said, each one of these would be squared off at the top, so it's not going to match the exact curvature here. All right, but if I do 15 rectangles, that's pretty good. If I do 25 rectangles, or that's better. If I do more and more rectangles, that gets better. And so how do I get the exact volume? Well, I do the limit as m and n go to infinity. All right, make more and more rectangles. And that is going to be equal to my volume exactly. Well, that just so happens then to be what we're going to call the double integral over region R of similar to what we did with regular integrals, right? Okay. So the volume under our surface or between the surface and the xy plane over whatever region R we want it to be over, okay? So here's what we got. Let's just draw R, and then I'll attempt to draw maybe the actual surface here. Just a rectangle. X runs 0 to 3, and Y goes from 0 to 2. So this is the region here we're talking about that we want to be our bottom part. Okay. So here's what they show then. Let's grid this off because we're dividing up into 6 equal squares, which happens then to be our delta x and delta y are both 1, so that's good. And we want the sample points to be in the lower right-hand corner here of each Rij. So our sample points, if you will, are going to be these of each square is going to be in the lower right corner. So just kind of dot those off so we'll know. All right. So the volume then is approximately equal to, in this case we've got the sum, the j's running 0 to 2, doesn't matter which, you can do the i's or the j's listed. All right, well, the good thing about choosing as we have, delta A is just the area of each little sub-square, sub-rectangle. So it's of each one, yeah. Remember, delta A is delta x times delta y. Okay? Now, ij star, and so that's where the sample points come in. In this case, what have we got for these right here? Well, we've got these points, the lower right corner. So it's 1, 0, 2, 0, 3, 0. Okay, so we're going to have this double sum is turns out to be f of 1, 0 times delta A. You write it all out. Just so happens delta A in this case is always 1, so not necessary, but we'll put it in there because it won't always be 1. And f of, what's the other ones? 1, 1. Okay. And so, yeah, this is very easy then. F of 1 variable function, so what will be f of 5? Okay. So this volume is approximately 7 and 15. Is that 62? 62. So it's similar to something we've done in the past there. Just got the complication that you've got two sums there.